Up to now, we have had lots of fun with kinematics, and we've kind of gone away from kinematics for a little bit, you've noticed. The kinematics equations are the straight line motion equations that we did in Chapter 2. Vf squared equals vi squared plus 2a delta x. My irrational personal favorite, delta x equals vi delta t plus 1/2 a delta t squared, all those. We didn't talk about those with our analyzing vectors. Well, everything that we did there, we said was one-dimensional. It was like stuff tied to train tracks, straight line motion. What happens if we start having things go like that? Uh-oh. Like if we flicked everything off the desk. We use those same kinematics equations to describe this kind of motion. No, not in the simple way we did in Chapter 2, because there's motion on both axes. We independently use the x-axis and the y-axis, but now for every single point on this object's path, it's got an x and a y component to its velocity, its acceleration, its motion. Ooh, this is starting to look like calculus. But we're going to do it all with algebra, so don't panic. The way we handle this little conundrum of ours is that we break apart the motion. Because guess what? You now know how to resolve something that's a resultant into its components. So we resolve all the vectors into components, and then we can use those equations that we have for one-dimensional motion on each axis. We even have ways to blend the axes, which will just blow your mind. It's fantastic stuff. It really is. It's cool. But we do have to resolve all of our motion into the two axes. So we're going to start, when we do these problems, listing our variables differently, which is a trick nobody taught me. I figured it out on my own, and it really helps. So first of all, let's define projectile motion. This is anything that gets launched into the air and that is only being acted on by gravity. And what this actually is, well, it's just free fall where we have some initial velocity on one or both axes. At this level of physics, we ignore air resistance. Go on to a college engineering program, you will no longer get that luxury. But for now, we can ignore air resistance. And so what we get are perfect parabolic pathways. My drawing is not perfect, but if we ignore air resistance, we get these very nice parabolas with very little distortion. So in that drawing, you can see that we have, and we'll just talk about the initial velocity. We have some VI overall, and that VI can be broken down into VIY and VIX. Note that we make really extensive use of subscripts here. You'll do your subscripts 2 deep. I don't think we get into any, 3 deep comes later, but be real careful about your subscripts. And VIY and VYI are both acceptable. I don't care. I tend to default to VIY, VIX, VFY, VFX. I think because that reminds me I'm working with the initial velocity and then I'm breaking it into components rather than working with a Y velocity and breaking it into components. Okay. This is the exact thing that you were talking about Mr. Voorhees doing in physical science with a bunch of squirrely, ornery freshmen. We look at 2 balls. We drop one straight. We flick one off the edge. As long as we aren't hurling this thing downward, you're not chucking it, you're just letting it fall, neither of these objects has got an initial velocity on the y-axis. One of them, however, has an initial velocity on the x-axis. That's the difference here between a two-dimensional motion and a three-dimensional motion. The vertical motion is just free fall. There's no other acceleration operating on the y-axis, and acceleration due to gravity only operates on the y-axis. Does that all make sense? Okay. These equations that you know and love so well are going to form the basis of everything that we're going to do. Okay, so we said that the red one's got no horizontal velocity and it's just straight up chapter 2 free fall. But the yellow ball has been flicked off an edge. That's why I flicked all those markers at you. So Vix is not equal to 0, but there's no acceleration. A sub x is equal to 0. Well, if there's no acceleration, the velocity is constant. The initial and final velocities on the x-axis are going to be equal. You could also add to that, if you were feeling like it, that the average on the x is going to be equal to vi. All the velocity on the x-axis is going to be the same. If there's no acceleration, then any velocity you want to look at on that x-axis is going to be identical. Okay. There are equations on page 100. We're not going to look at them. Those are the golden equations that we've used before. We're going to start off talking about horizontally launched projectiles. These are what I like to call kicked, flicked, and pushed. We're going to kick things off surfaces, we're going to flick things off surfaces, and we're going to push things off surfaces. At no point are we going to give them any initial velocity on the y-axis. So for all of these problems, VIY will equal, 0. Put my bar through the wrong thing. All right, let's do sample problem on 101. All right, we're told that the Royal Gorge Bridge in Colorado rises 321 meters above the Arkansas River, and you kick a little rock off the edge. The rock hits the water such that the magnitude of the horizontal displacement is 45.0 meters. Find the speed with which the rock was kicked. So this is where I have to have the whole little talk about patterns and discipline and organizing the mind. Math is a great tool for organizing your brain. If your brain's not already well organized, math can actually help you organize it, and for some of you that seems like a completely crazy notion, but it's true. When you do these kind of problems, because we have variables on two different axes, the trick that I sort of finally figured out myself after many years of fighting with it is that my variables list looks like this, which gives me the ability to separate those variables. So to start off, I'm going to just start by listing all the variables that I'm aware of. So I know that it's kicked, so VIY equals 0. VIX is what I would like to know. Now let's talk about acceleration. Acceleration on the x-axis equals what? 0. There is none. What about acceleration on the y-axis? It is equal to negative g or negative 9.81 meters per second squared. Hello, gravity, my old friend. I've come to talk with you again. I really should use the pause button for things like that. Do we know displacement on either axis? Yeah. So we're told that delta x, so if we trace this object's path, we're told that delta x is equal to 45 meters. Are we told delta y? Yes, because we're told that the bridge rises 321 meters above the river. So what is delta y? Be very careful here. Negative 321 meters is the displacement of the object. All right, find the speed with which the rock was kicked. So here's the challenge. We got two axes. We got variables on each axis. Could we write an equation for the motion on the x-axis using the four golden equations that we've got? Sure. So I have Vix, which we know is also equal to Vax and Vfx because there's no acceleration. It's just Vx. I've got delta x. What thing is generally connected to velocity and displacement? Time. To everything, turn, turn, turn. No, that's a season, not a time. Okay, so time. We don't know time. What about the y-axis? What do I have here? I've got initial velocity, I've got displacement, and I've got acceleration. Do I have a final velocity? No. I need at least one more factor on this axis. So here's the mind-blowing part. Acceleration is different on each axis. Displacement is different on each axis. Velocity is different on each axis. You know what you can't escape? Time. Time is the same on each axis, and time is what ties together the motion and the acceleration and everything else on the two axes. So I do this as a reminder to myself that time is the thing that's going to tie together our two axes. This was a huge breakthrough for me about 6 years ago when I realized that I had been doing this, but in terms of presenting it this way and in terms of thinking about it this way, listing it this way gives you that reminder that the thing that's going to tie together your axes is time. That's the thing that's in common between those two axes. So let's try to write an equation on the x-axis. We're going to just scribble that out because we don't have it. That uses time, displacement on the x, and velocity on the x. Well, we've got that lovely old chestnut. Back to basics. Vx equals delta x over delta t. As long as there's no acceleration, that's legitimate. Now, we could also, let's say we wanted to get fancy. Oh, let's get fancy. What the heck? You got a tie on. It's a day for being fancy. So what if I wanted to use my irrationally favorite delta x equals vi delta t plus 1/2 a delta t squared, and this is all on the x-axis. Anybody notice anything about this? Oh, this whole second part you say is going to go away because that's 0? Oh, that's kind of cool. So then if we recopy that, that would be delta x equals vix delta t. And this is vix equals delta x over delta t. Huh. Well, let's try to rearrange. Let's try to rearrange this to create an expression that is solving for delta t. So vix delta t equals delta x. Oh wait, isn't that what I just had there? Huh. Weird. Okay, so delta t equals delta x over vix. Well, now I have an expression that's all x-axis variables that I can plug in to use for delta t. Huh, that could come in handy. What if I write an expression, so let's see, I've got viy, a sub y, delta y, and delta t. It looks like I could actually use my irrationally favored expression again on the other side. So what if I did delta y equals viy delta t plus 1/2 a delta t squared. Anybody see anything magical that's willing to happen? Oh, look at that! This is 0, so that goes away. Boy, that's convenient. So now we have delta y equals 1/2 a delta t squared. Huh. Now, is there any way to... Oh, and this is, by the way, of course, a sub y, because we're dealing with all the variables on the y-axis. It's really important when you're writing these equations that when you initially write these equations, if you're starting off with a delta y equals, delta something equals vi something delta t 1/2 plus 1/2 a something, everything is on the same axis. Until you intentionally merge those axes, you have to be absolutely positive that all your variables are relating things on the same axis, or it's not a true statement mathematically. Well, you know what? We now have this, which we could jam in here. How stinking cool is that? I know. Okay, so at this point, we've got delta y equals 1/2 a sub y times the quantity delta x over vix quantity squared. What are we solving for? Initial velocity. Well, all our initial velocity is, of course, on the x-axis, so vix is what we're solving for. So now it's some algebra. Okay. And at this point, I would actually say we can get rid of the vix because we know, and I should have probably made a note of this, we know that vix is equal to vi, and that's what we would like to know. So the entire velocity here is on the x-axis. Okay. You got some more algebra up your sleeve? So I do this the slow way, vi squared 2 delta y over a y equals delta x squared, and then I can multiply both sides by ay, divide both sides by delta x. Nope. Okay, I had a momentary algebra brain fart where I couldn't see it. Sorry for the stall. So, okay, vi squared equals delta x squared ay, a sub y over 2 delta y. To get vi, we just take the square root of that whole mess. Let's plug it in. Okay, not so bad. 45 meters squared times negative 9.81 meters per second squared over 2 times negative 321 meters. Take the square root of the whole mess. Note that the negatives cancel out. That's handy. Okay, I'm getting a raw answer of 5.56 and change meters per second. Let's do a quick dimensional analysis check. We had meters squared times meters per second squared over meters. So that's meters cubed over seconds squared divided by meters. Okay, this is it. Tomorrow we're going to finish this up, touch base on a few things, and then all of the problems will be assigned.